secure. The third encryption method is one-way hashing, and with one-way hashing we have no reverse action. We take, in this case, some plain text, we put it through our hashing algorithm, and we cannot reverse the action, so it creates a hash signature. So in this case we take the text, and Eve cannot work out what the actual original text actually was. Typical algorithms are MD4, MD5 and SHA1. It's typically used, as we'll see in the next unit, to create digital fingerprints and in secure storage of passwords. An example here is with the Windows login authentication, where we take a password, it is then hashed with MD4, and then it produces the hash function. Another application is in the Cisco password storage with MD5, where we can create our secret password, and when it is displayed it is shown in an MD5 hash format with some salt. Unfortunately, hashing suffers from dictionary attacks, where it is possible for an intruder to generate a whole dictionary of words and the equivalent hash, and then looking up the hash to tell what the original message actually was. So to make this more difficult, many users change certain letters to make it more difficult to search through a dictionary. With hash signatures, obviously there is a finite number of signatures, so what can happen is a collision, and a collision is where a different message creates the same hash signature, and this, it might be possible to have what's called a collision attack, where an intruder creates another message with the same hash signature. More complex than this is that an intruder might be able to create the same hash signature with a similar context for the message. In some way the message has some of the information of the original and creates the same hash signature. And the most difficult, of course, is a full context where the intruder has managed to create the same hash signature and the message itself has the same context. And it was shown fairly recently in 2006 that the MD5, it is possible if you store hash signatures, and it takes less than a minute to actually produce the same hash signature. The calculation for this is for a 50% probability of a collision is the square root of the total number of signatures. So in the end it ends up 2 to the power of n upon 2. So for an MD5 128-bit, for a better than 50%, then if we store 2 to the power of 64 signatures, we'll have a better than 50% chance of a collision. One application of public key encryption is with encrypting disks. As we'll find